we are under the multiple linear regression setup, and you know that in multiple linear regression the number of regressor variables is more than 1, and in most of the practical problems what happen is that the number of regressors is very large, and having the large number of regressor variables, we may wonder whether some of them can be some of them are irrelevant and can be removed from the regression equation. Well, so the basic idea behind this finding the best regression model is that we need to find an appropriate subset of regressors that can explain the variability in response variable well, and finding this subset of regressor variable, this problem is called variable selection problem. Well, let me explain the thing in detail. There are several algorithms to solve this problem, and those algorithms can be divided into that can be classified into two classes basically. One approach is called all possible regression approach, and the other one is called sequential selection. Well, so first I will be talking about all possible regression. All possible regression. Say here we need to consider all regression equations involving say 0 regressors Well, so if there are k minus 1 is the total number of regressors in the multiple linear regression model, then the number of model having 0 regressors is k minus 1 C 0, and the model is basically y equal to beta naught plus epsilon. Okay. So, we will also consider, I mean, of course, the regression equations or models involving one regressor, and the number of models, number of such models is k minus 1 C 1, two regressors k minus 1 C 2, regression models are there involving two regressor variables. Well, similarly, we go up to k minus 1 regressors. So, number of models involving k minus 1 regressors is 1. So, total we have 2 to the power of k minus 1. . regression models. And you know, these models these equations are evaluated according to some suitable criteria. The first one is called R square. This is the coefficient of multiple determination or coefficient of determination, and then we will be talking about the criteria at just state R square, and then MS residual, and the finally we will evaluate the equations based on the criteria Mallow's statistic, and this one is denoted by Cp. Okay. And this is one approach, that is all possible regression, and the other approach is called sequential selection. So, I will be talking about this sequential selection later on, and there are three algorithms of this type. Those are called forward selection, backward elimination, and the stepwise selection. Okay, so today we will be talking about this all possible regression and how to evaluate so many, 2 to the power of k minus 1 regression equation based on these criterias. Well, now if the number of regressors is 4, so usually we denote the number of regressors by k minus 1. So, if k minus 1 is equal to 4, then k basically k denotes the number of unknown parameters in the model. Well, so if there are k minus 1 regressors, that means there will be k minus 1 regression coefficients, and there is another unknown parameter which is the intercept. So, total you will have k unknown parameters. Well, so if there are 4 regressors in the problem, then there are 2 to the power of 4 which is equal to 16 possible regression equations. And let me just I have those 16 regression equations. So, here I am considering a problem with 4 regressor variable. So, this is the model which without any, I mean with no regressor variable. So, number of such model is 4 C 0, which is equal to 1. Now, these are the models involving one regressor variable. So, this one is involving x 1, the second equation is involving x 2, x 3 and x 4. So, these are the 4 regression models involving one regressor variable, and then we have 6 regression model involving two regressor variables. So, this one is involving x 1, x 2, x 1, x 3, x 1, x 4, x 2, x 3, x 2, x 4, x 3, x 4. And then next we have regression model involving 3 regressor variables. So, there are 4 C 3, that is equal to 4 such models, regression model. So, this one is involving x 1, x 2, x 3 like that, and this is basically the full model. This involves all the 4 regressor variables. So, there are 4 C 4, that means one such model. Okay. So, when the number of regressors variable is 4, we have 16 possible regression models, and we need to evaluate them with respect to some criteria, and see the complexity of this approach. If you have a problem with say k minus 1 equal to 10, that means the number of regressors is equal to 10, then there are 2 to the power of 10, which is equal to 1024 possible regression equations. So, clearly the number of equations or the number of regression models that need to be fitted, that increases rapidly with the number of regressor variables. Well, so I mean, but still since in most of the practical problems the number of regressor variable could be like 20 to 30. So, but of course, you can use a computer to fit all possible 2 to the power of 20 models also, there is no problem. Well, so next I will be talking about the criteria. The first criteria I mentioned that criteria for evaluating subset regression model. Well, so we need to evaluate those subset models, and the first criteria to evaluate them is I mean one criteria is coefficient of multiple determination. And we denote this one by r square. So, before also I told I mentioned about this r square and we used to call it like coefficient of determination, and hence since we are talking about multiple linear regression model here, we call it multiple coefficient of multiple determination. So, we denote this by R p square. Well, so this let R p square denote the coefficient of multiple determination for a subset regression model with p minus 1 regressors and intercept beta naught. Well, so by R p square, this p basically stands for the number of unknown parameters in the model. So, since there are p minus 1 regressors, there will be p minus 1 coefficient and the intercept beta naught. So, total number of unknown parameters is equal to p, and we denote the corresponding coefficient of multiple determination by R p square. Okay. So, this R p square is equal to S S regression p by S S t, okay, which can be written as 1 minus S S residual p by S S t, right. So, what is this S S regression p and S S residual p? They denote regression S S and residual S S for subset model with p minus 1 regressors. Okay. And so, basically the R p square is associated with the model when there are p minus 1 regressors in the model, and R p square is a parameter which measures the proportion of variability in the response variable, which is explained by the regression model involving p minus 1 regressors. Well, so it is not, I mean, like R square, we know that R square increases as I mean, one observation you can make, that that this R p square, this R p square, it increases as p increases, because you look at the definition of R p square. R p square is equal to 1 minus S s residual p by S s t, and we know that S s residual this decreases as p increases. So, from here you can easily observe that R p square increases as p increases, and this is maximum when p equal to k, because p equal to k means p minus 1 is equal to k minus 1. That means, we are talking about the full model, and since we can have in the problem we have maximum k minus 1 regressor variable, and the S s residual it decreases as the number of regressor variables increases. So, maximum number of regressor variable possible is k minus 1. So, when this p is equal to k, S s residual has the minimum value, and hence R p square has will have the maximum value. Okay. So, what we do here is that we compute the value of R p square. So, basically first we compute R 1 square. This R 1 square is the case when the number of regressors is equal to 0. So, R 1 square means this will have, so p equal to 1, that means p minus 1 equal to 0. So, the number of regressors in the model is equal to 0, that is the model, if you consider the model y equal to beta naught plus epsilon. So, this is the model involving no regressor variable, and it is not difficult to observe prove that when you have this model with no regressor variable, then the coefficient of multiple determination is going to be equal to 0. Okay. Next, we will be computing R 2 square given a set of data. Okay. So, R 2 square basically here p minus 1. So, this is p. So, p minus 1 is equal to 1. So, this one is R 2 square is associated with the model y equal to beta naught plus beta 1 x 1 plus epsilon. So, this is R 2 square is for the model with one regressor. Okay. To illustrate all these things, first I will consider one example. Well, so this is quite famous data. This is called the Hald cement data. Here we have one response variable y, and we have 4 regressor variable x 1, x 2, x 3 and x 4, and we have 13 observations corresponds to the response variable and the regressor variables. Well, now here we have 4 regressor variables, and you may think that all the 4 regressor variables are not significant to explain the variability in y. Some of them might be irrelevant, and whether that some variables can be removed from the model without affecting the model predictive power. Well, so for that we need to select the regressor variables, which regressor variables are best to explain the variability in the response variable y. So, that is the whole purpose of this lecture. Let me explain the all possible regression situation here using this example. So, there are 4 regressor variables. So, these are the possible models. These are the possible models with 1 regressor. These are the possible models with 2 regressors, and these are the possible models with 3 regressor variables, and this is the model with 4 regressor variables. Now, what we need to do is that we need to fit each of them, and once you have the fitted equation or fitted model for this type of for involving x1, you can compute the SS residual, SS total, and from there you can compute the coefficient of multiple determination. Let me fit at least one equation. For example, I'll fit this equation. Okay, so I have this data. I'll try to fit a model between model of the form y equal to beta naught plus beta 1 x 1 plus epsilon, right. Okay. So, I will try to fit a model of the form y equal to beta naught plus beta 1 x 1 plus epsilon for that that Hall cement data. I am not going into the detail of. So, this looks like a simple linear regression model. So, you know how to find beta naught hat. So, you consider only the data corresponds to the response variable and the data corresponds to the first regressor variable x 1, and you know how to fit this model. Fitting this model means you have to find the least square estimate of beta naught and beta 1 hat. So, the fitted equation, you can check that the fitted equation is y hat equal to 81.5 plus 1.87 x 1. So, this is the fitted equation. So, once you have the fitted equation, you can compute the residuals E I, and once you have E 1, E 2 up to E 13, you can compute the SS residual. So, SS residual is going to be E I square from 1 to 13. You just check this is equal to 1 to 6.5. Well, so you have the fitted value, you have the original observation. So, from there you can get E, which is equal to y minus y hat. So, we know all these things, and the SS total is equal to, for this data it is 2715.8, and hence the SS regression is equal to 1450. So, I am just trying to give you some idea, given a problem with 4 regressors or 5 regressors, how to apply this all possible regression approach. Okay. Now, we can have the ANOVA table for this ANOVA table. So, the ANOVA table for this problem, I mean for this model is, you write the source of variation, degree of freedom SS, MS, and the F statistic, variation due to the regression model, total variation, the part remained unexplained residual. The total degree of freedom here is equal to 12 because there are 13 observations. Now, the SS residual, here you have 2 unknown parameters. So, basically you will be getting 2 normal equations and that means there are 2 constraints on the residuals. So, the residual degree of freedom is equal to 13 minus 2 because of the 2 unknown parameters in the model. So, the SS residual has degree of freedom 11 and the regression degree of freedom is equal to 1, and we have the SS regression value is 1450.1, residual is 1265 and the total is 2715.8, right, and the MS value is 1450.1 and the MS value here is this is 115.1 and the F value is equal to 12.6. Well, so what I want to say here is that once this ANOVA table is associated with the model y equal to beta naught plus beta 1 x 1 plus epsilon. Similarly, you have to fit the other 4 models involving one regressor variable, that means y equal to beta naught plus beta 2 x 2 plus epsilon. So, for that model you will get another ANOVA table. Similarly, you fit y equal to beta naught plus beta 3 x 3 plus epsilon, you will get another ANOVA table y equal to beta naught plus beta 4 x 4 plus epsilon, you will have the ANOVA table associated with that model. So, basically there will be 16 possible regression models, and for each of them you have to fit the model, you have to find out the associated ANOVA table for your convenience. Of course, you can use computer or some software package like SAS or S plus to do this job, and then once you have all this ANOVA tables or the SS residual value, SS T value for every model, you can compute the coefficient of multiple determinations. So, here the coefficient of multiple determination R square, and this is 2, here p is equal to 2 because there are 2 unknown parameters, and here r square is equal to r 2 square is equal to SS regression, which is equal to 1450 by 1265 by SST, which is equal to 2715. This is equal to 53.4%. So, here this model is not that good because it explain the model involving the regressor variable x1 only. This explains only 53% of the total variability in the response variable. Well, so what I want to say now, that look at this table here now. We have computed the coefficient of multiple determination for this model, that is 53.4. Similarly, you fit this model. This model is also involving one regressor variable, and that is x 2. You find out the corresponding ANOVA table, and then you compute R square value. Okay. So, this is the R square coefficient of determination associated with this model, and similarly you do for all the models. Here also you do for all the models. Here you can see that here this model particularly, it is a good one. This one is involving x 1 and x 2, and the coefficient of multiple determination here is 97.9%. That means, which is maximum in this class. So, among the two variable among the regression equations involving two variables, this one is best. This is that means y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus epsilon, because almost 98% of the total variability in the response variable has been explained by this model. Well, so similarly, you have to this is really a hectic job. Here you have to estimate all the models involving 3 regressors, and you compute the R square value for all the models, and this is the full model which involves all the 4 regressors, and the coefficient of determination is 98.2. Well, now what we want to do is that we want to draw a graph So, the number of regressor variable p, or basically p is the number of unknown parameters in the model along the x axis, and maximum R p square along the y axis. Okay. I hope you have observed that the higher the value of R p square, higher the value of R p square, better the model is, or the higher value of R p square, indicates better fit. Okay. So, what I want to mean is that out of all these 6 model which involve 2 regressor variable, this one is the best. Out of all these 4 4 models involving 1 regressor variable, this one is the best, because this has a maximum, this has the this model has the maximum coefficient of determination. Well, so what we do in this graph is that here all possible models with p minus 1 regressors are evaluated using the criteria, coefficient of multiple determination, and the one giving the greatest RP square is tabulated. Okay. So, let me take, this is my p equal to 1, p equal to 2, p 3, p 4, p 5. Now, when p equal to 1, that means there is only one unknown in the model, that means p equal to 1 means p minus 1 equal to 0, that means there is no regressor in the model. So, this is the model and the RP square value is equal to 0. Well, so here the RP square, maximum RP square is equal to 0. Now, for p equal to 2, p equal to 2 means the number of regressors in the model is equal to 1. So, out of these 4 models, the maximum maximum is 67.5. So, we will tabulate this one 67.5. Okay, suppose this is 20, 30, 40, 50, 60. Okay, maybe 20 and then 40, 60, 80, 100. Okay. So, 67.5, you can keep it here, p equal to 3. P equal to 3 means the number of regressors in the model is 2 and the maximum one is 97.9. Okay. So, we will plot this one 97.9. So, for 3 it is almost here. Now, for p equal to 4, that means the number of regressors in the model is equal to 3 and the maximum is 98.2. So, for 4 it is 98.2 and for p equal to 5 means there are 4 regressors in the model and the coefficient of determination value is 98.2 again. So, we will plot 98.2 here. Okay. Well, so what it suggests is that the algorithm is like that, you start with one regressor and add regressors to the model up to the point where an additional variable provides only a small increase in RP square. So, based on this stopping criteria, you can, this small increase means there is no specific value of this small, what you mean by a small increase. So, either this model with two variable, it has coefficient of determination value 97.9, which is close to 98% of the variability is explained by this two regressor variable. Now, if you go for the three variable model, then this one is the best, or also this one is also the having the same multiple linear regression model. So, clearly you do not need to go for the four variable model. Either you choose the three variable model, which is beta 1 y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3. Either you go for this model or you go for this model, and according to the coefficient of multiple determination criteria, this one is also not bad. This is a model with two regressors. Well, so this is how we evaluate the different possible, basically all possible models using some criteria. So, we talked about one criteria, that is the coefficient of multiple determination, and next we will move for the MS residual criteria. Okay. Residual mean square. Well, so what we know is that SS residual P, by P I mean this is the SS residual for the model with P minus 1 regressors, okay, when K minus 1 is the total number of regressor variables. We know that this one decreases as the number of regressor variable increases. And here we are talking about MS residual, which is equal to SS residual P, let me denote it by P also, MS residual P by n minus P. N minus P is the degree of freedom for the associated model, error degree of or residual degree of freedom for the associated model. Okay. And here one thing I want to mention that for SS residual decreases as P increases, but this is not true for MS residual. I mean MS residual may increase with P. Okay. So, the reason behind this one is that what I want to say here, let me write MS residual P, which is equal to SS residual P by n minus P, and also let me write MS residual P plus 1, which is equal to SS residual P plus 1 by n minus P minus 1. Okay. We know that SS residual P is greater than or equal to SS residual P plus 1, because SS residual decreases as P increases, but the same thing is not true for MS residual. Here this could be larger than the MS residual P. The reason is this, the increase in MS residual P occurs, I mean this may be larger, this occurs when the reduction in SS residual P for adding a regressor to the model is not sufficient to compensate the loss of 1 degree of freedom in denominator. Of course, what I want to say here is that this one is of course smaller than this one, but if you add an irrelevant regressor in the model, this will decrease, but the reduction here for adding one more regressor in the model, the reduction in SS residual is, if it is not sufficient to compensate 1 degree of freedom loss here, then only it increases. So, if you if the newly added regressor variable is not relevant for the response variable or not relevant for the model, then only the reduction in SS residual for adding this irrelevant regressor to the model is not sufficient to compensate the 1 degree of freedom loss in the model, then only MS residual increases. Well, so we learn how to evaluate all possible models using the MS residual criteria in the next class. Well, so we will continue this criteria MS residual in the next class. Thank you for your attention.